YouTube channel. And over the last few years, I've been deciding to create DSP or Digital Signal Processing Fundamental course, where my core objective would be to explain the fundamental concepts of digital signal processing, but not in theoretical way, more on practical way by programming them into the Python programming languages. So here I am today, and this is the outline that I would be following for this course, and this is the first video of the whole series on this course. So we will be starting with introduction of the digital signal processing. We'll define what signal is, what are its different categories, and then we will move on to continuous and discrete time signals and some famous concepts like convolution, correlation, and then sampling and quantization, then discrete Fourier transforms and some other transforms. Then we'll talk about filter types, and also we'll look at multi-rate signal processing, some further time frequency analysis, and adaptive filtering, and some other things. These are the books that I'll be using, and of course I'll be taking help from ChatGPT as well. And this is the first video. So without further ado, let's start with our first chapter of this series, which is related to really the definitions of really basic concepts in signal processing in general. So the first question is, what is a signal? Well, the easiest way to define a signal is, let's say in simple words, in our common language, is a signal is a gesture or a sign which carries the information. So if we want to define it in a way that a signal is some sort of way to present or represent your information that can change over time or space. So let's think of a message carried out or a data that is being transmitted and processed and then stored over the time in our daily life. There are several examples of signals in our life. In fact, one of our teachers during our undergrad course on signal processing used to say that basically universe is nothing without signals. Basically, it's the universe is basically a signal itself. It started with a signal, and then we have various signal types in our life. We can have sound in the form of the signal, we have light, we have a continuously changing temperature or even a motion. So if we say in simple words, a signal is like a pattern or a variation that carries the information. And it could be something that you can hear in the form of sound, your voice, or it could be something that you can see in the form of an image, or a video, or something you can measure. So signals are really important, which can be processed, and we can extract and learn meaningful information from those signals. There are several sort of examples which I've already quoted down here. Now let's look at some general characteristics of the signals. Well, signals mainly can be categorized into analog and digital signals, whereas the analog signal is something which is continuous signal, and it varies continuously over the time, and it takes the values within certain range, and it could be infinite as well, and it usually direct representation of the real world phenomena. So it is continuous both in time and value, can have infinite possible values, and we can have often representation of such a continuous signal, which could be let's say temperature continuously changing phenomena. Whereas on the other side, a digital signal is discrete. Well, it's represented by a chunk or the sequence of values, which in our electrical terms is called as zeros and ones, and they are represented at distinct point in times. It's like breaking continuous signal into small pieces and separate pieces. Their characteristics are like they are discrete in time and discrete in value. They are used in modern computers like smartphones and all these things. So everything that is based on electrical is basically signal. So our main or the core objective of the course is to basically practice these concepts in the Python programming language to see how these phenomena look like in visualization form, because when we look at some patterns, we memorize it well, and we learn them in a much better way. So we'll be talking about these two types of signals which we have just talked about, which is digital signal and the analog signal. And today we'll code the analog signal and the digital signal in Python to see how do they look like. So for this we use Python, which is a fantastic programming language, easy to use and easy to learn, and it has amazing libraries that are used to code these signals and plot them, and one of them is NumPy, and also the Matplot library which you use to plot the signals. So let's start with our analog signal plot or the presentation to see how these two signals basically look like. So let's call it analog signal, and for the analog signal, as we mentioned, that the signal is something that varies over time, so it will have some time, and if it's a waveform, will have a frequency as well and some kind of amplitude as well. So let's have a look at the analog signal. Let's say we have a signal in continuous time, and that's for example we have a signal between a starting point of 0 and 1 with 10,000, let's say, values. Okay, so an analog signal may be a sine wave, which could be, let's say, represented as follows. We say np.sine will have 2, and well, let's also define signal will have frequency. Let's define signal's frequency as 5 Hz. So we'll have in normal we say np sine is 2 pi ft as we normally define. So let's have pi, and then we have f here, and then we'll have this continuous time. So this is the signal with frequency 5 will be represented between -1 and 1 as an amplitude. This is the analog signal. If you want to plot, we can easily plot it, but let's go further with the digital signal. Whereas the digital signal is some sort of signal which is sampled. We take the pieces of the analog signal. In this case, or in our case, we take 100 samples, so we call it the sampling rate or the frequency of sampling, which is 100 samples. So we'll basically sample this analog signal, which is which has 10,000 samples between 0 and 1. We take its 100 samples in discrete form, and we'll plot this. That again we will see in the discrete form. So we need the time in the discrete form, and which should also between 1 sampling rate, and so endpoint is false. So this will give us 100 samples between 0 to 99, will not include hundreds itself. Then if you want to represent this digital signal, we can write it as np.sine to np.pi is normal f, and then we'll use here time discontinuous. So this is the same signal but in the discrete form with only 100 samples. But we want to look at this signals with its digital levels or quantization levels. So let's define quantization levels as 16. We'll define quantization and sampling in detail, but for the sake of representing these signals into continuous and its discrete form, we talk about the discretization or quantization here. So now we'll have a quantized signal after choosing 16 levels, which would be 4-bit quantization. So our sampled signal will have 16 different amplitudes between 0 to 15, which will be representing some sort of level or the amplitude in the signal. So we will take 16 signal levels, of this digital signal, and then so we first represent it between 0 to 1, between these levels, 0 to whatever the levels are, normalize the signal, and then we basically get this signals back to -1 to 1 level. So you will see that it would be plot inside that continuous signal, which will give us a much better representation. So this is how we represent this continuous signal into quantized or the discrete form. Now we just need to plot this signal into some form. So we'll use some libraries. Let's say 10 by 5 size of the figure, pld.5. So let's plot the continuous signal with the continuous time, or the analog signal. We label this as an analog signal, and we would like to see this in blue color. Similarly, let's plot the discrete or the digital signal with the continuous time, and we want to see its quantized form, and with some line formats. Let's look at this as the following, and maybe some markers as well. Just these are just things to make a signal look a bit nice. You can skip this, but it's much better to look at this. And then finally we will give it some sort of label, and let's also give it some title: analog versus digital signal. We also need to define labels. Let's call X label as time in seconds. Let's call Y label as amplitude, and let's also enable our legends, and let's also enable grid. Maybe looks nice, I normally do that. And let's show this plot, and we'll see what we have. Okay, so we have a little bit of problem here. We have -1 to 1, which is correct, but we have the signal between -3 to 3. Let's have a look at, maybe we did some, so no, this is some sort of incorrect thing. So we have analog signal, we have digital signal here, we have quantized signal, we have our analog signal here, and then we have some issue. So we don't see the positive side of the signal, and we need to figure it out. What is the error here? So we have the signal with this is perfect, and the only issue that we are having is only in the positive side of the quantized signal. We round the signal to, this is correct. Then we need to close this because this is not giving it. Okay, now perfect. So you can see that we have a continuous signal of 10,000 points between 0 to 1 in continuous form, and then we have our discrete signal, digital signal that we digitized and quantized. So each this signal represents the 16 levels between -1 to 1, and then we can represent this 4-bit quantization in some sort of digital zeros and ones. So it could be 000 and 0001 and then 0010. So these dots basically represent the discrete or quantization levels. So the quantization can have the error as well. I mean, you can increase this to 5-bit quantization level, you'll have better uh, representation. You can increase further to, so you can play with these levels by yourself to see how it changes. You can also increase sampling rate. So you see, when you increase more samples, you see the signals completely looks like continuous. So you can reduce it to 5, but it should be greater than this because already the frequency is 5, so it should be double according to the Nyquist theorem. To have a look at, you see, only really see few points, so you need to be more than the actual frequency is. So you see, when you increase to 50, you have some samples. But yeah, this is how you digitize the signal, and this is how these continuous and the digital or quantized signal looks like. And that is the difference. We have a continuous signal in time, where time and the signal itself is continuous, and but we have the discrete signal. We have pieces of the continuous signal into different instances of the time. So in short, if we want to summarize our first lesson, signal is something that represents information that changes over time. There are mainly two categories of the signals. Could be analog signal, it could be digital signal. Analog signal is continuous in both in time and value, whereas digital signal is discrete in time and discrete, and could be discrete in value as well, represented as zeros and ones. And we plotted these signals, and in the next session we will move with our next topic. For now, thank you very much for your attention, and don't forget to subscribe my channel. I'll complete this whole series of videos, and we'll just be focusing on the practicing or the practical side of this course. So thank you very much.